Hey guys, it is me, Cat Chemistry with my first ever video. Let me see. I wanted to disclaim first off, my editing isn't that great yet, and my camera is actually being borrowed from my animation classroom. I don't know why it keeps focusing and unfocusing for no reason. But it's an animation class. This is a science channel, okay, not a cinematography class, so it's fine. Today, I'm going to be starting off with atomic theory, my first part of 2 parts of atomic theory, because to know atomic theory, you have to understand this first part I'm going to be teaching. It's like the foundation, If you don't understand this, you won't understand what I'm going to be teaching in the second part. Okay, so let's keep this foundation steady. And first, I'm going to be talking about the gold foil experiment. Okay. Excuse my poor handwriting, but this is basically what the gold foil experiment was. So, back in 1911, Ernest Rutherford wanted to figure out what atoms actually looks like. So, he fired several alpha particles, which were basically helium ions, right here. Positive helium ions, at a super thin gold foil. He picked gold because gold is the most malleable metal. It's like, compared to diamonds, gold is Play-Doh. So, yeah, here's what happened. So most of the alpha particles just passed right through the gold, as if nothing was there, okay? However, a small amount did get deflected, a very small amount. The vast majority, just went straight through, okay? But some of them deflected in various directions, wherever they wanted to go, So, let me just draw that. However, an even smaller amount, like 0.001%, hit the gold, and then bounced right back to where they were fired from. Okay, so they would go, hit the gold, and then go straight back, like that. Okay, this led to 3 different results. Okay, however, in addition, this experiment debunked the plum pudding model, which was an atomic model of a circle with protons and neutrons just jumbled up all around it, which was proven to be wrong, but I'll explain that later. So these are the 3 main observations that Rutherford came up with, and these are the 3 main conclusions. The first is that atoms are mostly empty space. He found this because of the sheer majority that just went straight through, okay? Because you don't understand, it was like almost like tens of thousands of ions just went straight through as if nothing was there. Only a very, very small amount hit anything. It was the sheer amount that just went straight through, which proved that the atom was mostly empty space. Okay, if it were a little less empty space, then surely more atoms must have hit something, Okay, the second one is that in an atom, there has to be a positive charge, because for the positive helium ions to deflect off of something, that means that there must be a like positive charge for those helium ions to deflect off of, because like charges repel. Okay, and opposite charges attract. So, yeah. And the ions that just went back proved that the atoms, or the ions, that had to bounce off of something so small but so concentrated that it could send an ion straight back 180 degrees. Okay, which led to the famous model of atoms that we all know about today. Now, this is a classic example of the Rutherford model of the atom. Okay, this is an example of a neon atom. It has has a full valence shell of 8 electrons in its second electron shell. Okay, but let's take a deeper look at these actual electrons themselves. Okay, you see, electrons don't just float around aimlessly. Okay, they are actually organized into shells. Each shell designated towards a different energy level. Okay, think about an atom like a giant apartment complex or something, with electrons as tenants, or yeah, like that. Let me try to make this an analogy so that you and I can understand this a little bit better. Okay, so let's treat, as I said before, let's treat an atom like an apartment. Okay, electron real estate, where the electrons can be in their own orbitals, aka apartments. Orbitals equal apartments. Okay, and in each different floor of this apartment complex, there are different types of orbitals or apartments. A new type of orbital gets added to the already present orbitals, if that makes sense. Okay, the more floors you go, the more orbitals there are, the more electrons you can hold in a floor. Okay, so the first floor, or the first shell, can hold 2 electrons max. Okay, the second shell can hold 8, the third can also hold 8, but the fourth can hold 18, and it increases, so on and so forth. Okay, now, as I said before, not all quote-unquote apartments on a floor are the same. Each floor has orbitals, or different types of apartments. For example, let's go with the s orbitals, okay, or the sigma orbitals. The sigma orbitals are just like quote-unquote sigmas in real life. They have no friends, so they live in a tiny studio apartment with just themselves, okay, of 2 electrons. This equals, let me do it a little bit better. Let me do S and then the number above of how many electrons they can hold. So S2, if you can see that correctly. Okay, and then for P is on all floors after the second floor. Okay, so it goes from the second floor to the third floor to the fourth and so on. Or remember, floors equals shells, if that makes sense. So P6, that's how many electrons can be in a P apartment. Okay, for D, you can have 5 bedrooms, each room being able to hold a couple. Okay, so you can hold 10 people in a D apartment, and it keeps on going forever. And the last one I'll cover is F. Okay, which can hold 14 electrons. Okay, so 7 bedrooms, each bedroom being able to hold 2 electron couples. I'm sorry, each room in an F apartment being able to hold 2 electrons, a couple. Okay, this is basically what it'll be easier to understand in the molecular orbital diagrams. Let me give you an example of how a molecular orbital diagram is supposed to look like for sodium, as you can see here. So what I recommend you to have is a periodic table of elements, and on this periodic table there should be the atomic number. Okay, now the atomic number for sodium is 11, which means that there are 11 electrons. So that means that there are 11 tenants in this apartment complex. Okay, so first off, let's draw the first floor, or the first orbital, 1s, sigma. Okay, these are 2 little sigmas. Okay, 2 sigmas jumping on the bed, and they keep falling off and bumping their head. Now, this is on the second floor too. Okay, they have 2 sigmas here as well, but they keep to themselves. What am I talking about? Anyways, so now we have 4 of the 11 electrons, so we have 7 left. Okay, and remember the rule to not draw 2 electrons at the same room. Okay, draw 1 electron in each room before adding new ones. So we'll do this before adding new ones in each room. Just like that. Okay? Now we have 10 out of 11 electrons. So this means that we have to add one more sigma. Okay? Which is pretty simple. We just do this. Okay? We only jump up an electron when we have no more space to go in the already occupied orbitals. Okay? If we had an extra orbital here, if we had an extra electron here, I would not draw an orbital, an electron here, if there's already a free space here. Why would I? So you only draw it when it's completely occupied otherwise, if that makes sense. Yeah. Shown here is a molecular orbital diagram of silver. Okay, and this is quite a lot bigger than this one for sodium that I was looking at before. Okay, now there is no real shortcut to drawing this, at least that I know of, but what you can do is, for the electron configuration, we know that this will be a painstaking process to write down all the electrons for, because you're going to start with 1s2, and 2s2, 2p6, 3s2, all the way up to 4d to a maximum of 10, which you don't need to do that. Okay, it's not necessary, because everyone knows that silver is going to take up at least a vast majority of these electrons. Anyone that doesn't even have any chemistry knowledge. So what you can do is take a shortcut called noble gas configuration. Okay, and this is in which you refer to the nearest noble gas that is still smaller than the atom you are trying to take a shortcut to itself, and then take that atom, which in this case would be silver, krypton, and then you add the extra electrons to get a full electron configuration for silver. So what we would do is actually write down in brackets krypton, or Kr, and then 4d10, and then 5s1. So basically, we are showing that the electron configuration for silver is basically the electrons that you would need to configure krypton plus 10 and 1 electrons. So it's basically a very efficient and accurate way of a shortcut. When you are making a molecular orbital diagram, you must abide by 3 simple rules, just for better accuracy and efficiency, just to make sure that you get everything right. The first one is to fill the lower apartments first, okay? Because people would rather like to spend less money on an apartment, so they would go to the lower floors, okay? So they'll all stack up one floor at a time before going to a second one. They wouldn't skip any floor or anything like that. No. Okay. The second rule is to fill each apartment with 1 electron at a time, and then when you are done with that floor's apartments, then you can start putting roommates in there, because why would you put roommates in the same apartment when there's already an apartment that's still vacant, or is it non-vacant, whatever the term is, you know what I mean. Okay. The third rule is that if you do have roommates, they must spin in opposite directions. Okay, and if you don't get what that analogy means in real life, okay, because my roommates spin in opposite directions, but if you don't know, then you shouldn't know. Whatever. This is an example of a copper atom's molecular orbital diagram, and as you can see, anyways, what I'm going to be going over now is exciting an atom. exciting an atom is, I'm being honest, I can't really think of an analogy for this related to what I was talking about before, so I'm just going to be literal. I'm just going to be literal about it. In an atom like this, when you give it energy in a way or another, like lighting it on fire, the atoms, okay, the electrons, they get excited, okay, and this leads to them going up in energy levels. Okay, this is a fire, something I don't freaking know. That's a terrible fire drawing. Okay. Anyways, this fire heats up the electrons, and with enough energy, it can lead to some of the electrons going up orbitals. Okay, so these two orbitals will jump. Hold on. These two orbitals will jump up. These two electrons will jump up orbitals to 4p. Okay, so instead, it looks like this. Let me draw it now. So yeah, it looks like this. Wait, what the? It looks like this because these two electrons have left and they're up here now. Okay. However, I want you to note there is no right or wrong way to draw an excited atom as long as you have the same amount of electrons. Okay, so I can make these two atoms go up here, or I can create new orbitals even higher up, or I can have all of the orbitals go up to freaking 5, or I can make them all go to 5s and 40 and 5p if I wanted to, but I don't want to. Okay, there is no right or wrong way to draw an excited electron because it solely depends on how much energy you put into the atom itself. If you put in more energy, more electrons will go up. If you put in less energy, less electrons will go up. If that makes sense.